Amazing. Okay, nice. Thank you. Okay, I'm just gonna repeat everything just for the recording. So this is problem 2, and we have 2 approaches. We try the first approach first. So the first approach, we get a recursive relation, and by testing small cases, we see the first coefficient are 1, 2, 3, 4. The second coefficient is the set of triangular numbers. So reasonably, you can give this to be NC plus, well, that would be n times n minus 1 over 2. And you can prove that by induction, or I see that this equation, I can rearrange it as this, right? And now I can just sum up everything from, if I repeat the same formula, that and fn minus 1 minus fn minus 2 plus c, so on, until f2 minus f1, that would be 1 plus c. So if you add up everything on the left, we get fn plus 1. In fact, let's start with the second one because we want fn. So fn minus f1. On the right hand side, we get first term is triangular numbers added together. Sorry, I mean the positive integers added together. That's n minus 1 over 2 plus n minus 1 c. And hence fn is nc plus this. So we get fn, but must it be the final answer? Because our recursive relation here, we plugged in m equals 1. So it's a very specific case of the given functional equation. So we must test back this answer and see if it works for all m and n. So once you get your answer, do not think that it must be a valid one. You must test it. So now let's test. In fact, I'll just test it here. So m plus n, you get this term. Is it equal to mc plus this over nc plus this plus mn? Let's see if that's true. So we're left with m plus n squared minus m plus n over 2 equals m squared minus m plus n squared minus n over 2 plus mn, and that is correct. Yeah, you can expand it out and see it's correct. This is true. Hence, that will be a solution for this equation. So C is obviously a positive integer. So now let's try a second approach and see if it works. Can we try to eliminate mn by giving a new substitution or something? So how do you suddenly spawn an mn out of nowhere? Can we have like fx minus something? If you notice, this thing squared, you get m squared plus n squared plus 2mn, right? So what that tells us is if you kind of subtract on the left-hand side this quantity, you kind of subtract on the left-hand side this quantity, that means you're subtracting this side, this quantity on the right-hand side. And maybe you can cancel off the mn. That makes sense. But there's only one mn, so let's divide everything by 2. Let's divide everything by 2. You get this. So if we subtract, we get this very nice relation. Square over 2 plus n square over 2. Sorry, fn minus m squared over 2 plus fn minus n squared over 2. And the mn's cancel. So what can we see here? If I let this to be gmn, then we get a Cauchy equation. So I define Gn to be Fn minus n squared over 2. And we must be careful because now G is from n to z. Which doesn't make much a difference because Cauchy will still work. Right. Yeah. So now G is a linear function. You can test that if you're not convinced. You can test it. Let's say G1 is C, and then you find G2, which must be 2C and 3C and 4C and so on. So Gn must be Cn for some positive integer. Sorry, we're not sure if it's positive or not. So for some integer C. Therefore, Fn follows easily. So it looks a bit different, but I believe it's the same thing. But we have to find the properties for C because we have to make sure F is from n to n. Right, the domain is the set of natural numbers, the codomain is a set of natural numbers. And we immediately notice that C must be a half integer for this to work. For example, if n is 1, we get C plus 1/2, right? C plus 1/2. So C must be some sort of half integer. So let's just write C as a minus half, where a is positive now. And everything follows after that afterwards, and you can probably find the general solution. So Kn minus Kn over 2 plus n squared over 2. That would work. Is it equivalent? Oh wait, sorry. K minus 1/2. So that's so that's Kn plus n minus 1 over 2. So the same answer, 2 different approaches. Any questions? Or any other approaches you might want to consider and you're not sure if it works or not, so you can propose it and try it out. Okay, if not, let's try the next one. Okay, someone asks, does plus mn on both sides of the original equation also work? What do you mean? So, oh, okay. I'll just paste the question here if you don't mind. So here we have, if you add mn on both sides, you get this. But then if gx is fx plus x, it can't be, right? Like, how would you define this as a new function in terms of m plus n? So you want a function where you can kind of unite. Like if this is n plus n, then this must be in terms of n plus n, so that you know gx is, that's it. Yeah, so you have this. Okay, so let's try the next one. So the next one is a fun one. It's called Jensen's equation. Let me see it. So here I'll just require you to find the rational version. The real version, same thing. You can generalize it if you want. You can find conditions where you can say it's equal to cx or whatever. So Jensen's equation is x plus y over 2 equals the average of x plus y, or fx and fy. So for all xy rational. So this one looks very far off from Cauchy, because you want Cauchy, you want fx plus fy. I mean, okay, not that far off in that sense, because on the left hand side you have a sum. You have a sum of x over 2 and y over 2. But on the right hand side, you're not given the sum of fx over 2 and fy over 2. But instead, you're taking fx and fy together over 2. So how would we resolve this? So what we hope is, in fact, let's just equivalently double everything up. Then it will look nicer, right? It will be 2x and 2y. So on the left hand side, we have fx plus y. On the right hand side, we have this weird thing. So what we hope is, let's see. Yes. Okay. So someone gave a correct approach. I think this works also. Let's see. So I hope it's Cauchy. And yes, then there's a second approach as well. So let's focus on this approach first. Can we say this is equal to this? This is from the definitions, from the equation. And this one is where you let x equals y equals x plus y over 2. I mean, a equals b equals x plus y over 2. Which is correct. Yeah. Yes. So that's a clever substitution. So you substitute. So this is by substituting xy. Actually, just xy. And then the second one is by substituting xy as x plus y over 2, x plus y over 2. And then you get a Cauchy equation. And then you're done. Wait, is it? It doesn't seem right. Xy. Oh wait, it doesn't, right? Okay, sorry. This one's a bit false. You don't get this one if you substitute x and y as the same as the same. you get both sides is equals to 2. Yeah, so this approach doesn't work. You get this instead. Because on the left hand side it's an average, on the right hand side it's an average also. So you get this. So this doesn't lead you anywhere. Doesn't lead you anywhere. I mean this, at least this sentence doesn't. But yeah, so someone gave another clever substitution, which I will not spoil first. Let's see how we can get that substitution. So what we want is the right hand side to be, so what we hope is the right hand side to be fx plus fy instead. Right, we want to transform it to a Cauchy equation. What we hope is this. And what's the condition for this to hold? I mean, what's one of the conditions for this to hold? And hence what we further hope is simply f2x is 2fx, right? What we hope is this. Okay, so now let's see if we can prove this. And if we can't, let's see how we can fix it. Anyone has any idea how to prove this? Or at least some attempt to substitute some nice values of x or y to get this? Sub x equals 0, y equals 2y. Yeah, so I mean, if I transform this into y and 2y already, so you just have to substitute x is 0 or y is 0. So let's just put y is 0. So this is f2x plus f0 over 2. And so we have a bit of a problem here. It seems that we are almost there. 2fx is f2x but plus this little junk, which is f0. So now what we hope, or we further hope, is f0 is 0. But can this hold? Must this hold? If we put both sides as 0, we get a very frustrating result of getting 0 equals 0, which doesn't lead us to anywhere. But if we further inspect this equation, what happens when you shift f and yeah, so yes, so we have to shift f, and as you can see, if I let g be f minus some constant, let's say 10, right? Let's say 10. Both sides still are the same, because on the left hand side you minus 10, on the right hand side you minus the average of 10 and 10, which is still 10. So by shifting, you can always get a new solution. So f0 equals 0 is not something that we need to hope, but we need to force. So here, let's just let gx be fx minus f0. So that everything here is the same, but we have a further condition that f0 is 0. I mean g0 is 0. Okay, so here is where we get a clever substitution of gx equals fx minus f0 by studying the equation. So if I let this substitution be true, then we get gx plus y equals gx. I mean, we can reverse everything we've done. So we get g2x equals to gx. So we get gx plus y equals gx plus gy. And so by Cauchy, we get gx is cx, and thus fx is cx plus f0, which I will just call d. So fx is just the linear function. There are many ways to motivate us to substitute g equals f minus f0. Another motivation is you start to guess the solutions, right? And you find out that any linear function works. Like any linear function works, ax plus b. And so you cannot just hope to transform it into a Cauchy equation. You have to kind of shift it so that you can become a Cauchy equation. So yes. So let's look at the next one. So this is 3, right? Wait, is it 3? Yeah. And then the next one is for f r to r and f. So here's where I up the difficulty. X f y plus x equals xy plus fx. So now, this is obviously not Cauchy, and most of the exercises here are quite unrelated to Cauchy also. So what can we do first? Let's try a few values, right? Like if you've nothing to do, we just let y be 0 or something. Or let's let x be 0. If x is 0, f0 equals 0 plus f0, which gives us nothing for any y. So let's just write down, don't let x equals 0, because whatever we do, we put in x equals 0, it gives us nothing. Okay, how about y equals 0? Then now we have fx0 plus x equals 0 plus fx. Okay, interesting. So we have this equality. Yes. So someone has an opinion. So we can start directly see subjectivity here, right? How do we? Because there's a lone variable here again. There's a free variable, lone variable, naked variable, whatever. So subjectivity. Well, we can let's say let x equals 1. Then fy plus 1 is y plus f1, and the right hand side is of course something that we can shift anywhere on the real number line. So subjective. How about injectivity? Again, we make sure we can get this right. Let's say x is 1, I think. Yeah, use the same thing, use the same equation. So if fy1 equals fy2, substitute them in and you can get y1 equals y2. So that's injective. Okay, so this is injective. And now, what can we do when it's injective? F0 equals 0, yes. So cancel out the F. So we can cancel out the F. X F0 plus X equals X. So X F0 is 1. Sorry, is 0 for all X. So simply let X equals 1, then we get F0 is 0. So now we have F0 is 0. We should never let Y equals 0 again, because that's what it tells us only. Okay. What can we do next? Okay, so someone has an idea again. So let's look at this equation here. This is x times fy plus 1 equals this. Wouldn't it be nice if you just find a way to annihilate this term? If we do, we should get some relation between x and fx by substituting a suitable value for fy. And of course, we want it to be -1, right? We want this whole thing to cancel. So let t be f equals -1. It exists because of subjectivity. And hence f0, which is 0, equals xt plus fx. And hence fx is minus tx, or I mean cx. So the cx work? Let's just check. So c x cy plus x equals xy plus cx. And c squared xy must be xy. So c squared must be 1. So c is +1 or -1. And these are all if and only if conditions. So both cases should work. Yep. We'll take some time to digest this. Notice how we attack the problem by its weak points, weak points. For example, this one we can straight away demolish. And directly when we see this thing, maybe we can think about subjectivity and objectivity. Okay, let's try the next one. Okay, so the next one, again, FR to R. If it's just R to R, I'll just not write it. But we have this symmetric sum, which is greater than or equal to 3 times fx plus 2y plus 3z. So here's a tricky one, because now we have an inequality and we are expected to find an absolute equality for fx. But all we are given is an inequality. And the only way we can transform an inequality to an equality is where we get to know A is at least B and B is at least A, and therefore A equals B, those sort of things. So let's try to force such a relation out. So yeah, we have to kind of squeeze it also. So what would be a nice substitution? Let's try substituting some random variables again. Let's say z is 0. Then fx plus y plus fy plus fx is more than or equal to 3f plus 2y. Doesn't seem to help. And in fact, what we want is something to do like A is more than or equal to B, and then B is more than or equal to A, those sort of thing. So we want something that can work on both sides. And can that happen? Okay, someone said try xyz, substitute it as xx minus x. Okay, let's see what happens. I'm not sure what happens, but let's see. So 2x plus f0 plus f0 equals 3f x plus 2x minus 3x. Okay, oh sorry, there's some more there. And this, of course, gives us f2x is more than or equal to f0, which is nice. So we know all of the fx's are more than or equal to f0. Can we do something else? Can we get f0 is more than or equal to something? x0, 0. Yep, so someone gave a substitution x0, 0. What does this give us? This is fx plus 2f0. So f0 again. More than or equal to 3fx. And yes, indeed, f0 is more than or equal to fx. And therefore, fx is just f0. So the constant function, c. And let's check if it works. So constant plus constant plus constant more than or equal to 3 times the constant. Yes, so that works. Okay. The next one is also a little bit of inequality. Is it FR to R? Yes, it's R to R. So we have fx is less than or equal to x, and the fx plus y is less than or equal to fx plus fy for all x and y. So what can we do here? In fact, let me see if I can find a symbol. So any information we can extract from these two conditions. Oh yeah. This was a typo here. This should be fx plus f0. Yeah. Well, still same result. Okay. Now, as someone said, if you put, say, y equals 0, then fx is less than or equal to fx plus f0. So 0 is less than or equal to this. But by the first inequality, this is less than or equal to 0. So first thing we can say, f0 is 0. In fact, I might be going too fast. So let's just give everyone a minimum working time of 3 minutes. So everyone doesn't suddenly get spoon-fed the solution whenever someone else gets it. So we'll come back about after 3 minutes and see what everyone can get. If you got something, you can just tell me. I will just resume the class. I mean, you can just chat it. You can type in the chat, and then I'll see. But then I will resume after 3 minutes. Okay. So fx plus y less than or equal to x plus y. Yup. Okay, so the first thing I saw, I mean, one of the comments, I mean, yeah, the comments is this thing is more less than or equal to this, which is less than or equal to x and y respectively. But this doesn't tell much, right? Because this inequality is just this inequality. So nothing much there. Fx, okay, that's an answer claim, so I'm not going to read it out first. Substitute fx less than or equal to x into the second inequality and set y equals to 0. What do you mean? Oh, someone asked something about the previous question. May I ask how to get the conclusion of fx equals to c in the previous equation? So to answer your question, the first substitution, this substitution gives us that fx is more than or equal to f0 for all x. So of course this means simply by substituting x as x over 2, this means this. And by a second substitution, we get that f0 is more than or equal to fx. So these two implies that fx must be equals to f0, which is a constant, so I'll just rewrite it as c. So I'm not sure how fx less than or equal to x can give you fx equals to mx plus c. Okay, so someone gave this, which is at least something new and true as well. So this is 2fy. So I'll just put it in x because it looks nicer in x. And the setting, yes, so then the following comments is all about taking x and minus x and then finding the symmetry, right? So let's say we, let's say put y equals minus x. Then f0, which is 0, less than or equal to fx plus f minus x. Okay, another question. How do you get in the previous question to the conclusion that 0 is between? Which one? Okay, not the previous question, this question. This one. Okay, I see. So this one is from here. And then since fx is less than or equal to x, f0 is less than or equal to 0. So f0 is 0. Okay. So yes, we get f minus x is more than or equal to minus fx. Okay, so here's the claim. Here's the thing we can do. So we apply this again, inequality here, to both of these variables. So fx is less than or equal to x. And also f minus x is less than or equal to minus x. Well, it's true because I just substitute x as minus x. I'm not multiplying both sides by -1, just substituting x as minus x. So that means this thing is less than or equal to x minus x, which is 0. And hence fx plus f minus x equals 0. Okay, there are a few ways to finish up the solution. And one of them is given by you is, okay, so f is odd, f minus x is so f minus x less than or equal to minus x, meaning minus fx is less than or equal to minus x. So fx is more than or equal to this, but fx is less than or equal to s. So fx is x. Okay, another way you can finish it from here is to just notice when can equality hold. If you want this equality to hold, that means both of these must hold. So fx is x and f minus x is minus x. That also works. So again, it's just about manipulating the terms and then try to move them around. And whenever you have an inequality, what you hope is you find some symmetry. So a less than or equal to b, b less than or equal to a. Okay, any more questions? May I know how to get 0 less than or equal to? So may you know how to get this one? Well, I'll substitute this. So this is from this substitution. So y, I let it to be minus x. So this thing becomes f0, which is 0. And this is fx, and this is f minus x. And so we have this. Yep, you're welcome. So it's all about substituting the right values, and intuition plays a very big role in such a decision. So of course, experience is quite important. So try to practice more to get that idea or intuition that you can have. Okay, any more questions? Well, if not, you can try the next one. The next one is this one. So again, f is from R to R. Okay, again, I will let you guys have a minimum period of time for you to work with, so you can play around with the equation and try to see if you can find any information from here. So good luck. We will return at, well, 15:35 or maybe 32, 33. That's exactly 5 minutes from now. May I ask, in Q4, how do we check injectivity? So Q4 is this one. Oh, injectivity. Okay. So we use this equation, and we see the left-hand side is entirely in terms of Fy, right? So what that means is, if Fa equals Fb, I can just reconstruct this whole term here. I can reconstruct the whole term here. So Fa plus 1 equals Fb plus 1. Apply F on both sides. So now you can say this is A plus F1 is B plus F1, and hence A equals B. So you utilize the fact that the left-hand side is entirely in terms of Fy. So whenever you have Fy1 is Fy2, you can say they are the same for both cases on the left-hand side. And so on the right-hand side, they are the same, and so the y's are the same. Okay, you're welcome. Is fx squared, no. Normally f squared x would be f, but fx squared is just literally fx, the whole thing squared. Okay. Okay. So any clues that you found? Yep, F is injective. F is injective. So injectivity, how do we prove injectivity? Take advantage of that lone variable y, and then we let x equals 1, for example. Then this is or f equals 0, or f equals 0. So this is ffy equals f0 squared plus y. And this implies injectivity and surjectivity both at the same time. So hopefully you can see it immediately by now without me writing the whole procedure again. Because the left-hand side is ffy, so whenever you have fa equals fb, you can kind of transition it to the right-hand side. And the surjectivity, because this is anything, any real number. So it's bijective, so f is bijective. What next? So there must exist z such that fz equals 0. Okay. And if we let f0 is z, okay, so let's put z on both sides and see what happens. So on the left hand side, we have z times 0, which is 0, and fz, which is 0. So that's 0, f0. On the right hand side, we have z. Okay, and hence ff0 is fz is 0. But ffy equals f0 squared plus y. So f0 is 0. Yep. So f0 is 0. How does that help? ffy equals y. Yep. Okay. So ffx is x. This is what we call a convolution. Where is it? Something probably called a convolution. So basically ffx is x. And the convolutions are obviously bijective. Yeah. So what can we get here? Okay, now we see okay, so we let y is 0, then we get this. Okay. So how do we get rid of the annoying square? Oh, and substitute y to be fy. Very, very interesting. So this would become course, this is y, this is fy. And this is very similar to Cauchy, yes. Very, very similar to Cauchy. f1 squared equals x. How did you get that? We put f1 squared. By substituting x as 1. Well, if you substitute x as 1, you substitute on the left side and the right side also. Okay, I'll just write it here. So if I put x equals 1 here, we get ff1 equals f1 squared, right? And of course, ff1 is 1. So f1 is either 1 or minus 1, which is great. Lastly, notice that this implies that since f is surjective, x fx. But the thing is, if f is surjective, doesn't mean x fx is surjective. So counterexample, let's say fx equals 1 over x or something. Or even fx equals x. It won't go through the negative numbers. But now we have this very nice condition. f1 is 1 or minus 1. Isn't x fx f of something? Is it? Well, if fx is x, then how would you explain x times f is surjective? Like if fx is x, then this is x squared, and it doesn't go to the negative numbers. Or even the worst case 1 over x, then x times fx is 1, which is not surjective. If we substitute x equals 1, we can get Cauchy. If we substitute x equals 1, we only get f1 plus fy equals 1 plus y. I don't think that works. For Cauchy, you have to have 2 variables. Okay, so here's something that I would try. I will try to let x become fx. Then x fx becomes fx ffx, which is just x fx. So that's the symmetry popping in. And the right hand side gives us x squared plus fy. And so we're almost done here. So comparing these two equations, we get that fx squared is x squared. And hence fx is x or fx is minus x. But again, this is a pointwise trap. So maybe there are some parts that obey the first rule, there are some x's that obey the second rule. And we we'll try to avoid that happening. Okay, so yeah, this is quite important because it directly transforms this into that. So in fact, there are quite a lot of things that we can ignore from the proof. So for example, this one, I don't think we need this. The one case. And this one also, oh wait, this one we need, and then x becomes fx. Okay, if everyone's okay, we can move on to resolve the pointwise trap. So how do we resolve the pointwise trap? So we say fa is a, so some x obeys the first rule, and fv is v, so some other x obeys the second rule. But of course, we have to kind of make our lives easier. Because what if a and b, one of them is 0? Then, because if anything is 0, then it obeys both rules at the same time. And indeed, f0 is 0, as we've shown up there. So just to avoid any sort of confusion, we say where a and b are non-zero. So whenever a becomes 0, that means a contradiction. Or b is 0, we get a contradiction. Oh, sorry, this is fb equals minus b. Sorry. So you want a to obey the first rule, b to obey the second rule. But we want a and b to be not 0, because only when it's not 0 where you have to make a choice. When it's 0, it obeys both. So AB is not 0. Now, what we can do is just try to plug it back in and see if we can get a contradiction, right? So let's see if we can get a contradiction. Well, let's just try xy equals AB, because why not? So the first case, the first bracket, is a times fa, so a squared, and then plus fb, which is minus b. So this, and the right hand side is a squared plus b. How did you get fb equals minus a? No, fb equals minus b, because you want b to satisfy this. Yeah, so you don't want a and b to kind of obey. I mean, you don't want one x to obey the first rule and another x to obey the second rule. Of course, we try to hope to see that we cannot do so. So we say, let's say a fulfills this one and b fulfills this one. So we see what happens. And we get fa squared minus b is a squared plus b. But we know that fx is either x or minus x. So what does that mean? That means either a squared minus b is a squared plus b, or a squared minus b is minus a squared plus b. Either case gives you 0. And hence we are done. Therefore, either all x satisfies fx equals x, or all x satisfies fx equals minus x. Of course, you have to check, but I'll just leave that job to you. Quite a simple thing to check. Wait, this is quickly glance through and see if it works. X squared plus y. Yep, and if it's minus, It works. It works. It works. Okay, any questions? All right, then let's move on to the next one. So this, well, problem 7 is a bit harder than the previous ones. Let's do problem 8. Problem 8 looks very much like Cauchy again. So x squared plus y equals fx squared plus y, right? Yeah, plus fy. Okay, again, so what can we do here? Well, again, sorry, I should give you the 5 minutes minimum working time again. So let's discuss this at, well, I'll give you more time for this one. So we'll just discuss it at 4 o'clock then. And again, if you have any questions, you can ask anytime, including now. Okay, so I have a few comments already here. So here we, first of all, most of you got this. So fx squared equals fx whole thing squared. And that allows us to prove this x squared plus y, fx squared plus fy. And this is very much like Cauchy. However, x squared must be non-negative, isn't it? So how can we make sure it works for negatives as well? So what we can do is, let's say I let y equals minus x squared. Then, let's just rewrite this first. This is just fx plus y equals fx plus fy, where x must be greater than or equal to 0. Where's the greater sign? There we go. How do we get the entire Cauchy equation from this? So how do we allow for negative x's? So to do that, let's just let, well, I can let y become y minus x, where x is greater than 0. Then this becomes fy is equal to fx plus fy minus x. Okay, let's just prove it's it's even first, or odd. If I let y become minus x, then f0 equals fx plus f minus x. Okay, what's f0? So that's the next question. You can plug it here. f0 equals f0 squared, meaning f0 is 0 or 1. I don't think 1 will work. Yeah, in fact, you can just plug it back. You can just plug it here. Plug x is 0. Then fy equals f0 squared plus fy. So f0 is 0. So back here, we get 0 equals fx plus f minus x. So f is odd. So this one becomes f minus x plus y equals f minus x plus fy, where x is greater than or equal to 0. Oops, sorry. So here we go. So combining these two, we say fx plus y is just fx plus fy for all x and y. And that's Cauchy. So in fact, Cauchy actually still works if you just restrict one of them to be positive and also make sure that f is odd. But here's the thing, f is from R to R. So how do we make sure we know that fx is cx for all the real numbers? So remember what we did the last lecture, we gave 3 conditions. The continuous one, probably not very useful. Very hard to see f is continuous from these equations. So it must be the bounded one. Can we see any bounded interval? I mean, any interval on which f is bounded, either from below or from above. In fact, we use this one. So what does this say? This says fx, f a positive number is f a non-negative number equals a non-negative number. So this implies fx is greater than or equal to 0 on the interval, let's say just 0 to 1. And so f is bounded from below on some interval. Therefore, fx equals cx for all x. So here is where you can use what we've learned just now. If it's bounded on some non-trivial interval, then you can generalize to the real numbers. Okay, the next one's quite satisfying. Ninth question. So f is r to r, and you have this one. Okay, let's give you 5 minutes to think of any ideas. How many questions do we have left? Oh, we have 3 more. Wow. But I'll give you 5 minutes and hopefully you can find any nice things about this equation. Okay, so I got some ideas. So if we put y equals 0, then we get f squared x equals fx squared, which I think doesn't really help much unless probably not. But this problem pinpoints on a very important step, and once you get over that step, you are basically done. And the step is to notice that these two terms can be forcefully cancelled. How? Because we can make fx plus y equals x squared minus y. So when does this happen in particular? It happens when y is x squared minus fx over 2. Is it? Yeah. So in particular, if we let y be this particular value, plug it back in, those two terms must cancel. Those two terms must cancel. 0 equals 0 plus 4fx and whatever this is, x squared minus fx over 2. And we just have two cases left. If so basically fx is 0 or fx is x squared. Now, of course, this is another point-wise trap, and I think this one is a bit harder to resolve, but let's just treat it anyway. So fa is 0 and say fa is 0 and fb is b squared. And hopefully we can try to force a contradiction. And again, where a, b are non-zero. Because if it's 0, then both cases are true. So xy, ab. Let's quickly substitute this in. 0 plus b is b squared. The right hand side, f a squared minus b plus 0. So either b squared is a squared, either b squared is 0, which is false, or what? Or a squared minus b squared is b squared. And this means a power 4 minus 2a squared b is 0 and a squared equals b. And we're not done yet. Let's see. fa to fa squared. Now we can use this condition, I think. So f squared a equals fa squared equals b. fb. And this is b squared. But what's fa? Fa is 0 equals b squared. 0 equals b. So, I mean, the pointwise trap, after the pointwise trap, you can probably find some, just plug it back in and just force a contradiction to occur. So now, we can repeat the solution. So fx is entirely 0 or fx is x squared. But I think this one, you don't really have to use that step. But I think that step can simplify the step a lot more. Okay, and we still have 15 minutes left. Let's try to finish the last two, which are presumably the hardest. I'm not sure when I did the questions, they seem to be the weirdest, but but still doable, I think. So the 10th one, f is from, this one's a bit different. So it doesn't want you to find all. It doesn't want you to find all. It just wants you to construct a function. Where fx, fy equals fx over y. So we just want to construct one function, that's all. And of course, if it asks like that, then, well, fx equals to 0. Wait, hang on. Oh, sorry, positive rational numbers. Positive rational numbers. So positive rational numbers. So you cannot put fx is 0. So this is true for all xy, where y is non-zero, of course. Oh wait, I don't even have to write y is non-zero because it's q plus to q plus anyway. So anyway, let's just see, we plug in some values and see whether anything is useful. So we put x equals 1, we get this. We put y equals 1, we get this. And all right. So f1 equals f1. Does injectivity work here? It does, right? It does, yeah. So this one implies injectivity and surjectivity quite directly. You can check that. Because f1 is non-zero, and then, well, I'll leave it to you for that, to prove that this is injective from here and surjective. So that means f1 is 1. That means f1 is 1. Okay. So ffy, or ffx is 1 over x. Now from here, I think we can start to construct already. Is there any way to construct such a function? We want to bring x to somewhere, and then if I apply it again, it suddenly becomes 1 over x. Any ideas? One minus 1 over x didn't work. So 1 minus 1 over x didn't work. Here's the thing. Why did it say q plus to q plus? Why didn't it say r plus to r plus? There must be something that's going on that only applies to q plus to q plus. So I claim you can try to operate on primes. And let's see if that works. So if you operate on primes, then kind of every rational number is kind of like a product of primes, right? On the numerator and the denominator, product of primes. And also, I think if you notice very carefully, sorry, I think there's also one more information that is probably useful to know. Let's say I put y equals x, then fx, ffy. So sorry, y equals fy. So x times ffy, which is this, equals fx over fy. And hence, fa fb is equal to fab. So it's multiplicative. And that's why I said you want to operate on the primes. So you kind of want the primes to obey this relation. And if you notice, these two actually are equivalent to the original equation. If you have these two are correct, then you will apply this. So you know you just have to satisfy these two properties. Multiplicative and f of x equals 1 over x. So let P be a prime. We want to try and see what can we do to this prime P such that if you apply it twice, you get 1 over P. And also if we, oh yeah, so this is another technique before we end the class. This is another technique. It's called the triple F technique. Triple F technique. Sounds a bit weird, but this is what you do. Fx, you apply F outside, which means you get this. You apply F outside, and then you apply the F inside. So that will be 1 over fx. So one I apply the substitution x become fx, and the other I just directly apply f on the outside. It's called the triple F technique because you involve 3 f's and then you look at it from the first two or the last two. And this means, well, this is just a consequence of, it's just a consequence of the multiplicativity. So P is a prime, then maybe I let FP be some other prime Q. And I let Q, maybe I'll just write it in this way. P, I become Q, become 1 over P, become 1 over Q. Maybe become P again. Yeah, seems okay. So I let P1, Q1, P2, Q2, blah blah be all the primes. Then I define FPI to be QI and FQI to be 1 over PI. I think this should work. Hopefully. So let's just check. FFPI is obviously 1 over PI. FFQI is F1 over PI, which is 1 over FPI, which is 1 over QI, yes. So it works for all the P's and Q's. And every rational number can be uniquely written as a product of primes above and below, and therefore we are done. So this one is another quite weird function where you have to assign a value to each of the corresponding important inputs. So in this case, the primes. I try to define f for the primes because if I do, then I can manage to define f for every single rational number. And so if you can write it out explicitly if you want. So the rule of f is f, well, you can just give some prime factorization above P1 to the A1, PQ1 to the, okay, it's a bit fussy to write this all out. But you can do in paper. And then this would be 1 over, well, Q1 to the A1, Q2 to the, sorry, P1 to the minus B1, and blah, blah, blah. So you can write the relation out explicitly if you want. And then you can just check to them that this works by plugging back in and chasing the prime factors. So I guess we have only 2 minutes left, so I probably don't have time to do the last one. And the last one is also quite fun, actually. If you want to try at home, you can, I don't want to spoil any hints now. If you're stuck and you want that solution or something, you can just message me or on Discord or something. Then if that's the case, any more questions? What's the difference between P and Q? Good question. Well, there's no difference. So basically, I just label the primes in this order in pairs. So I can just say this one is 2, 3, 5, 7, 11. So 2 is my P1, 3 is my P2, Q1, 5 is my P2, 7 is my Q2, 11 is my P3, 13 is my Q3, and so on. So because I write it in this way, so that I can have this cyclic relation when I define the function. So FPI is QI, FQI is 1 over PI. And of course, there are infinitely many primes. Any other questions before we end the class? Any other questions? So the function has different definitions for primes in group P and Q. Yeah. So a function doesn't have to be something that has a pattern. The only thing you want for a function is that every input has an output. So it doesn't matter what kind of output you give to the inputs. So the reason why I split it into two groups P and Q is because I need this relation to somehow hold true. And the only way I can think of is to create this sort of cyclic thing where I have a P type of number and a Q type of number, and I just cycle through P and Q. And indeed, it kind of works. So I had to try and error for this. Of course, I didn't do the checking step, but I think it's doable by just using this explicit form of the function. Because this is the solution. This is the solution that you can, well, one of the solutions that you can give. It is you are allowed to write it like that because it indeed gives a rule of how you define f. Because every rational number can be written this way, and then you just say the output is this according to this pattern. Okay. Any other questions before we end the class? If you have any questions, if I have any questions about this handout later, may I send a message to you on Discord? Yes, absolutely, sure. In fact, I insist, if you have any questions, you can just ask me. And I will reply you when I'm free, of course. But eventually I will reply you. So any other questions before we end the class? In fact, if you have a question, please just type it in so you have a question, because I know it takes time for you to type a question. So if you write I have a question now, then I can wait for a few more seconds for you to type out a question. Okay, so if there's no questions, then I'll end the class here. It's been a pleasure and honor and privilege to be here. And I'll see you probably a few weeks later. So the next class, I'm not sure who will be teaching. I think it's Nelson. So yeah, tomorrow I'll be teaching the beginners. So okay, then goodbye.